Okay, here's another homework problem. It's a theoretical yield problem. You'll notice that we have two givens, and that sucrose is our dude over here. We'll get those circled right now. And that ethanol, the other given, is one of our products. So we've got a given, we have a starting amount that we're going to figure out how much ethanol we're really going to get after we figure how much we could get. Okay, so how much can we get? And who wants to tell me, what do I start with? Given over 1. Which one? Sucrose or ethanol? Why sucrose? That's the reactant, yes. Okay, so we go our 684 grams of sucrose over 1 times, okay, here we go, C12. Someone get out a calculator, help me out here. Let's get the numbers in quickly. C12, Justin, you do C12, and
I'll do hydrogen.
good, okay. Yeah, right, thanks. You're a big help. How about oxygen?
176.
Okay, just a second. H22 is equal to 22. And Justin, what was this one? 144. Let's just use round numbers here. And oxygen,
176.
what?
176.
176. Okay, and we get 2 carry the 1, 6, 7, 7 14, carry the 1, 3. Did I do that right? Okay, 314 grams is equal to 1 mole of sucrose. Okay, so we're here. We're going to get this guy, and we're going to go down here, and we're going to get sucrose, and we're going to start. I'm shortening this stuff just so you don't get lost in all the writing. Okay, this stuff is easy to get lost in. Now, if you're not writing this down, you really got to screw this. This is what's going to be on your test today. Okay, so our number from right down here, this guy is going right here. So this is our 342. And what's going to go on top? 1 mole of what? Of sucrose. Okay, and I'm going to start off by circling that. Before I even look at anything else, I'm going to write moles of sucrose down here. And now I have my head on straight. So, what is my mole ratio? Sucrose is going to be what? See, it's right here. What's sucrose going to be? 1, okay. And the other guy is ethanol. And this is moles. And the number is 4. Okay, now we're down at the bottom of the triangle, right? We just did the bottom of the triangle. We got moles of sucrose, took us down to the bottom of the triangle on the left, and then we did across to the right, and we got our moles of ethanol, and we threw that back up to the top line. I'm talking the chart now, right? And we are now in the middle of the chart at moles, and we're going back to grams. Okay, now we got to do that again. So we're going to have 2 carbons, 14, 14 or 28. Everybody know what I'm doing right now? Yeah. Okay, that's off the chart. And then we got hydrogen 6. Oops. I'm sorry? Yes. Yeah, carbon is 4. Carbon's 12. Yeah, 24. Thank you. And then our hydrogens, there's 6 back here. Okay. Those carbons, the hydrogens are 6. And we've got oxygens at 1. 1 oxygen is going to be 16. And we got 12, 16, 1, 3, 46 grams is equal to 1 mole. So, before I did this, I should have done this so that I don't get anything out of order. And I've got moles of ethanol And up here, I'm going to have what? Okay, so what's the number that goes with moles? 1. And the number that goes with the grams of ethanol? ETH, short for ethanol, is 46. Okay? Okay, here we go. Calculator's out. The first number is going to be 684. That's on the top of a fraction. And on the bottom of the fraction, we tell the calculator it's on the bottom with the what? Divide sign. And that's going to be 342. And then we tell the next one with a what sign? 4 is on the top, so it's times. 4. And 46 is on the top, so it's times again. And then we hit the equal sign. Our number that I get is 368.
I didn't just do 684 times 4 times 46.
All right, now let's go ahead and finish this thing off. We go back to or we look at the top, and I'm going to extend this page, I think. Yes, I'm going to extend it. I want a little space to make this spread out plenty for you. Okay, we want the theoretical yield, but first, we got the theoretical yield. That's what we just got when we got our number. And what was that number? Okay, 368 is the theo. And that was grams. And what was the actual? 349. Okay, so again, this one went pretty close. 349 grams is the actual. And we multiply this by 100. Get any of this stuff mixed up with the other things. Oops. Oh well. Whatever. And now we're ready to do a division. Somebody have a number for me. 94.8%. And that is our percent yield. That's our second answer. Okay? Okay, this is another problem that feels very much like stoichiometry. And in this case, we don't have a balanced equation. What we have is simply a mole ratio of one element to another within a molecule. Okay? That molecule, when we get billions of them, we call that a what? Compound. Okay? So we're trying to find out what part of that compound, or how much of the part of the compound that is oxygen is going to be how many grams. Okay, so here we are. We've got to get this into moles, and I've started the problem already. We know the given, we know the find, and the given over 1 is where we started, and we got to here, and I decided that we'd record this so that we have it for today's lesson. And so now we did this stuff down here to figure out how many grams are in 1 mole of this sucrose. So what's the number that goes down at the bottom along with the grams of sucrose? Yeah, okay, so this is going to be 180. And on the top, what are we going to have? 1 mole. Of what? C6H12O6. All right. Okay, what can we do next to get closer to our goal? That's our first step. Right. Good. C6H12O6, and we'll circle that again. And let's go ahead and cross both of these guys out. And now we have to figure out what 1 mole is of what? What's our mole ratio? Okay. What is the mole ratio going to be? See, this is where it gets to be stoichiometry, right? Yes. 6 O's for every molecule. Okay? So we take the molecule itself and we say, okay, if I just look at the oxygen part, what is my ratio of 1 molecule to oxygen? Atoms of oxygen. So now we have, what's this? Okay, right. This guy's going to be 1, and up here we're going to have oxygen atoms. Right? And this is going to be moles of oxygen atoms, and the number is 6. Am I making sense?
Would the bottom moles change if there was a coefficient?
No, would not change with, oh yes, it would change with coefficient.
So the bottom moles?
Oh yeah. If we wanted to know what the ratio, actually the ratio would wind up being the same. But I'd have to tell you how much I actually started with. So I said in this case we're starting with this many grams of the sucrose. That would, yeah, because there's no coefficient because there's no balanced equation. So coefficients wouldn't play in here. Yeah. Good question. Very good question. All right. Let's go down now. And what is our next fraction going to be? I have moles of oxygen atoms. Am I getting close? Huh? Am I getting close? Huh? Can I smell the end? Huh? Oh, moles down here of oxygen atoms. There we go. And now we can cross this out. And my number to go to oxygen is what? How many grams in a mole of oxygen? 16. Okay, so that's our number up here. And it's 1 mole down here. And this is oxygen atoms. Okay? Looks a lot like stoichiometry, doesn't it? And I was just figuring the makeup of a molecule. Let's go ahead. So we're going to work the numbers out, and what I want you to do is stop the recording and go ahead and run the numbers on this calculation on your own. Okay, now that you've done that, I'm going to do it with you, and you can check yourself and see if you did this properly. So we'll bring up just the numbers without the whole mess of stuff that we're looking at right now, and we'll run the calculator, and I'm going to this time go straight across because this is another method that you may wish to choose. You may find it less confusing. So I'll put in the first number. That's 125. It would be on the top of the fraction, and so I'm going to go across. So this is going to be times 6 times 16. And now the next number's on the bottom. So now we tell the calculator that with the divide sign, and we put in our 180. And the number I get is 66.7. We'll round that, and that will be the number that we have for the answer. 66.7, and that's going to be atoms. Oh, grams. Yeah, grams. This is grams of oxygen atoms. Now, what if I wanted to know, I've got grams, what if I wanted to know the number of particles? How many actual atoms? Who do I use? Avo. And I would shove that in right at this point, right after this guy. Instead of going back to oxygen atoms, this is 16 grams of oxygen atoms. Oops, there we go. Okay. So, yeah, we got it there at the end. And if I wanted to go to oxygen particles, then instead of using this, I'd use the Avo. When I said this, I was pointing to this guy. Okay? So we could go either way with this. Okay, we're discussing, I'm just starting the recording, we're discussing intermolecular forces, which Justin properly identified as force between molecules. To understand force between molecules, we have to understand that polar molecules are magnetic. They have magnetic personalities. No, they're just magnetic. And the reason they're magnetic is just like before, we have unshared pairs on the central atom. That makes this guy magnetic. What's another way that he might be magnetic? Besides unshared pairs on the central atom. Here we go. Let's look at this guy. Does this look familiar? CO2. Is this guy going to be polar or nonpolar?
None.
He is nonpolar. Why?
There's no molarity.
No unshared pairs on the central atom. So the unshared pairs on the central atom aren't there. So, because the oxygen on one side and the same atom on the other side, there's no difference in electronegativity between this oxygen and this oxygen. So if there's no difference in electronegativity, that means there's an equal tug here on this side and on this side. Please do not be doing anything else. You need to understand this. Now, let's contrast this to carbon with sulfur on one side and oxygen on the other. Since sulfur and oxygen are in the same column, they have the same number of valence electrons, and their Lewis structures look identical. As soon as I get the right Lewis structure. Okay? Their Lewis structures look absolutely identical. This guy, CO2, is nonpolar.
Always?
Absolutely. This guy over here is polar. Can anybody guess why? Yes, the oxygen and the sulfur and the carbon, oxygen, sulfur, I don't know exactly how that would be named. But at any rate, on this guy, the molecule is going to be polar. Let's see, who has the greater electronegativity? Oxygen. So oxygen is going to be pulling stronger. Oxygen's pull is this way. We're talking about in relationship to the carbon now. And sulfur is actually going to be coming that way as well because he's not as strong. And so carbon in this bond, carbon in this bond is going to get more of the electrons. So we're going to have a partially negative side and a partially positive side. Partial because the electrons aren't transferred. Okay, that's the lowercase Greek letter delta. Okay, the capital delta looks like a little triangle. And when I'm trying to write things in shorthand, I say delta instead of change. But delta is going to be a positive charge or a negative charge. There's going to be a change in the charge, okay? A change of some sort. So the electrons are being funneled over towards the left side of the molecule, which makes it a little more negative over here and a little bit positive over here. This is going to be a weak dipole, but it will be a dipole. This is called a dipole. Polars, molecules have dipole moments. You know, it's kind of like a Kodak moment. No, not at all. Not even close. But it's fun to think of it that way. The dipole moment simply means that somehow this molecule, this CO and S combination, is going to wind up polar because it is not what we call symmetrical. You ran into this in one of the labs we did recently, right? Remember that? The reason why it was a particular shape was also the reason why it would be polar or nonpolar. So we're just extending this a little bit. Now, if we look at water, this guy is polar. So does he have a dipole moment? Yeah. Yeah. Who has more electronegativity, oxygen or hydrogen?
Oxygen.
Oxygen. So where is it going to be negative? On the oxygen side. So this guy will be a partial minus, and the hydrogens, each of them will be partially positive. And did I show you the little animation that shows the dissolving of salt? Oh, we're going to have to see that. So when something dissolves in water, it requires the stuff that it's dissolving to be polar. Now, what we need is plus any charged particle will be dissolved in water. Let's watch how that happens. You have a salt crystal in the middle. That's right there. And what's happening? Water molecules coming in. Bing, taking those little dudes away. Oh, it's ganging up on them. Whoa. Now, let's look at the solution. This is after all the salts dissolve. You notice every particle of salt has been surrounded by water molecules. Now, let's go back and see a close-up view. Oh, now, ooh, who's going in towards that piece? Positive end or negative? The negative end, yes. The negative end of that water molecule. See, this shows the dipole moment. And it shows the positive end is over there between those hydrogens. And the negative end is at the tip of the oxygen, furthest away from the hydrogens. So that's the side that's going to have the negative charge, which when it gets around that little positive charge, which is one whole positive charge, or maybe two, depending on the piece, that positive charge can collect a lot of water molecules because they're just partially negative on that end. Let's try that one more time. Watch it again. See them coming in? Negative side going towards the center. So who has to be in the center right now? Sodium or chloride? Sodium. Why sodium? Because he's positive. That's right. Good. Okay. Let's go back. Now, what is your prediction when we do it with chloride? We're going to go after chloride now. Which end is going to go toward the molecule? Watch them. See it? The hydrogens are going in first. And who has to be in the middle? Of course, the chloride. So that's how you see things being dissolved, and you'll also see intermolecular forces. Okay? Now we're going to take a look at different states of matter, and we're going to relate it to intermolecular forces. Intermolecular forces because the forces between these guys have water lined up. Have you noticed how it's lined up? Look where the hydrogens are here and where they are here. So the negative end, well, as soon as I start writing here, it'll go away. It'll stop moving. But right here, this guy is the negative end, right? And this guy is the negative end. And this is lined up with the little positive ends. Partially positive, of course. I can't write small enough to make that work. But you notice that this guy is a positive end that comes towards the negative end. And this guy, his little positive end here is going towards this negative end here. And so they are being attracted to each other. Without that intermolecular force, people, we would have no rivers, we would have no oceans. This would be a different Earth. And we wouldn't be here because we wouldn't have water to drink. You can't go without water very long. You can go longer without food, but you can't go without water very long. And so as you check this out, in this little animation, you're seeing now the solid state. When I add energy to these molecules, what happens when I up the temperature? What happens to the shaking here? More rapid. Yes, excellent. More rapid. As that becomes more rapid, there will come a point where it starts to melt, and then the water's going to look like this. It moves around. It's having a hard time getting off the surface because the intermolecular forces are holding it. That's why we have rivers and oceans and lakes. Without that, without those intermolecular forces, no rivers, no lakes, no ocean, and this is a very sad place to try and make a living. Okay? We don't do very well. Now, if we give this enough energy, in other words, we're upping the temperature. When we up the temperature, now we get into the gas phase. Okay, that happens at a higher temperature. Why? Because the water has to change to gas, and that happens at what temperature in centigrade? 100 degrees centigrade. Have you ever looked at a boiling pot of water? Where do the bubbles form? On the bottom.
And they rise.
And they rise to the top. Yes, they do. But they form on the bottom where it's the hottest. And that's where the water is being changed from liquid to gas. And you require energy to do that. CO2, no problem. Minus 60 degrees, it goes to a gas. And by the way, CO2 goes directly from solid to gas. That's what dry ice is. Yes. Dry ice is just CO2. And the intermolecular forces are practically nothing. They're more than what you would have with hydrogen, which is totally nonpolar, okay, because the hydrogens are both the same electronegativity. It is a higher temperature to get to the gas than would be with nitrogen. Nitrogen is at minus 180 as a liquid, and then it'll go to the gas phase. Okay? So those intermolecular forces is what I'm trying to get through to you right now. Okay, we're going to do page 388 from the homework, number 3, which is one of the more difficult conceptually of solving these rate problems. If we turn to page 387, we see the rate thing, and we see this formula. Rate A over rate B is equal to square root of what? What is it, folks? Molar mass. Molar, M-O-L-A-R, molar mass of what's on top? B. Over the square root of the molar mass of A. Notice we have the crisscross relationship. That means it's inverse. Okay, so as the rate of A goes up, its molar mass is down. And didn't you see that in the gas simulator when we were doing Dalton's law? You notice that big old honking chlorine molecule, atomic mass of 71 versus the little old hydrogen molecule, which was a molar mass of 2. Okay, it was a lot faster, wasn't it? That little baby was just bouncing all around off the walls and off everything else. Okay, where that big old chlorine molecule was just like a big sumo wrestler trying to walk across the room. And, you know, the sprint guy was just dashing all over the place. By the time the sumo wrestler gets to the other side of the room, the sprinter has gone back and forth 10 times. right? Okay, that's like the hydrogen versus the chlorine. Okay, so let's look at this problem. And now, Christine, would you tell me what is given?
You are given 3.6 moles per minute.
3 point what?
6
3.6 what?
moles per minute.
Moles per minute?
Did I say it wrong?
Yeah, that's what it is.
Oh, as the diffusion rate. Okay. Rate is equal to 3.6 moles per minute for what?
For B, rate of B.
Okay, this is going to be the rate of B. She called this the rate of B. All right. And what's the other one? What else is given?
It says that it's twice that of a gas of B. It doesn't give anything else.
Okay, what is the rate of effusion of a gas that has 2 times the molar mass? Okay, yes?
Moles per minute.
Moles per minute. Moles per minute. Yes, thank you. Okay, and now what is the rate of effusion of a gas that has a molar mass twice that of a gas that effuses? Okay, so this gas we're going to say is B, and the rate of B to A is, let's see, that's twice that of the gas that effuses at. So the gas that effuses at the 2 times is B. And this guy, or is A, I'm sorry, and this guy, B, where's that? Only gas twice that of a gas that effuses. So the B is the 3.6. Yes, okay. So A is twice B. Would that be fair to say?
It says the molar mass of B.
The rate of effusion of a gas that has a molar mass twice that of the gas that effuses at the rate of 3.6. Yeah. Okay, so this is the relative molar masses. Are we clear of what's going on? Okay. This guy, A, is twice that of the guy that effuses at the 3.6. So what are we supposed to find?
The rate of diffusion for A.
Okay. The rate of A. The guy that's twice as fast, right? Okay. So this, you got to keep your head on straight. The very first thing you have to do in a problem like this is label A and B. If you don't label A and B, you're dead. You'll never get this right. You have a 50-50 chance of getting it right. So let's fill in the formula. Okay, the rate of A is what we don't know. Am I correct here? What is the rate of B? 3.6. And that's moles per minute. Okay, is equal to the other side. What is the molar mass of B? Molar mass of B has got to be up here, correct? Molar mass of B and molar mass of A. So what's the relative rate? A is 2, and our molar relative mass is A is 2 and B is 1. So I'm going to substitute those in. So A now is at the bottom, and that's 2, and B is at the top. So that's 1. Does it matter what the exact mass is of either one? It's only the relative rate, or the relative mass in this case. Okay? Once I have the relative mass, it really doesn't matter, because I'm going to get a ratio of the masses of the two things that we're talking about the rates of. So this is where we'll call this rate A x. He's the unknown, and this guy is 3.6. Now, this is the trick that I was telling you about yesterday. Squared, squared. Now, why did I do that? Get rid of that radical, right? So, now all we have to do is solve this little dude, and we get x squared over 3.6 squared is equal to 1/2. So, someone give me 3.6 squared? Okay, so we got this guy at 12.9 times. There we go. 12.9. 12.9, and that's this guy. X. 12.96 by 12.96 is equal to 1/2. Okay, so I'm going to divide 12.96 by 2, correct? So x squared is equal to 12.92, and divided by 2. 96, thank you. Okay, and so we take this guy and figure out that is, what was it? 6.48? Okay, now we got to take the square root of both sides and we're done. Yes? So x is equal to the square root of 6.48. And we can do that on our calculators. The number comes out. Our answer, once we take the calculator and do the square root, we're going to round this to 2.5. So the rate is 2.5. What's the unit of measure for the rate? Moles per minute. And that's what they want for an answer. Yes? On page 415, hold on, there we go. All right, we're working on problem 514, number 63 from tonight's homework. And we're going to see what the relative rate of effusion is of these two guys. So they wanted the ratio of effusion of krypton to neon. So the rate should be like this, krypton to neon. So on the other side, what do we have? Molar mass of neon. Neon's on top, right? Molar mass of krypton. Right? So, plug in the numbers. What's neon? 20.18?
Yes.
Okay, that's neon. What's krypton? 83.80. And that's still in the square root, dude, right? So, we want to divide and take the square root. So, all right, when we run the calculator and do the magic that the calculator does for us, we find out after we divide 8.380 into 20.18 and square root, we get the relative rate of effusion as 0.491. Now, the ratio of the rate of effusion of krypton to neon required us to have krypton on the top. So this is the rate of krypton to the rate of neon being compared. And when you do it that way, you're going to find a 0.491. And does that make sense in terms of their molar mass? You bet it does. Yeah? I'm sorry? 3 is fine. I just did 4. It doesn't matter. Because you only need 3 sig figs in your final answer. Yeah? Because the ratio of krypton to neon, that means krypton's on the top. That's how you know. And if krypton's on the top on the left in the rate areas, then the molar mass of krypton has to be on the bottom in the square root area. Okay? That's how it works. You're done. Done deal. Very, very simple question on this one.